Welcome to the deep dive. Imagine for a moment, what if intelligence isn't merely a complex dance of computations, but something that behaves like physical matter, like following the fundamental laws of physics, and even resonating with the harmonious precision of music? And here's the real kicker. What if the key to unlocking true brilliance, to sparking explosive creativity, isn't about remembering more,
Right.
but about strategically, intelligently forgetting?
That's the audacious territory we're exploring today. Our mission is to unpack a truly fascinating collection of sources that reveal what researchers are calling a thermodynamic foundation of cognition.
Thermodynamic, like
Yeah.
heat and energy.
Exactly. We're going to dive deep into how memory, forgetting, and even abstract mathematical constants like pi and the golden ratio aren't just influences or metaphors, but are literally the fundamental forces that sculpt the very nature of intelligence itself. We'll be walking you through cognitive thermodynamics, this astonishing idea that strategic forgetting equals sparsity, and the profound, almost poetic concept of harmonic intelligence.
Harmonic intelligence. Wow.
Yeah.
Imagine your mind less like a rigid silicon chip and more like a dynamic system capable of existing in different states. Just like water can be solid ice, flowing liquid, or invisible gas.
Right.
Each of these cognitive states, we'll see, has its own unique properties for processing information, for remembering, and for creating.
Does sound a bit out there at first glance.
But we're going to show you exactly how this revolutionary perspective is being demonstrated with empirical evidence.
Yeah, the data is pretty compelling.
Okay, let's unpack this truly shocking discovery. The idea of intelligence, not just like a physical system, but as one. We're talking about something called cognitive thermodynamics. This isn't just a clever analogy, is it?
This is where it gets really interesting. Fundamentally redefines the playing field, you could say.
Okay.
The core concept here is revolutionary. Intelligence literally follows thermodynamic laws. Literally. It's not just an analogy where we say, oh, it's kind of like that. No. It's described as a literal structural isomorphism.
Oh, okay, isomorphism, like a one-to-one mapping.
Exactly. Think of it like a universal blueprint. Whether you're building a physical engine or a cognitive one, the underlying thermodynamic principles apply in the same way. This means our minds, or really any intelligent system, behave like physical matter. They undergo phase transitions, just like water turning into ice or steam when its temperature or pressure changes.
Phase transitions in thought.
Yeah. We're moving from observing intelligence to understanding its fundamental physical mechanics.
So my brain is like a kettle or a cloud.
It really does.
And you're saying memory decay is something we've been taught to see as a flaw, a sign of aging or inefficiency. That's actually a crucial, active part of this system.
Exactly right. Memory decay isn't a bug, it's a feature. A really important one. It's like temperature in this cognitive system.
Temperature, okay.
Think of it this way. Higher decay rates mean a higher cognitive temperature.
Right.
Just as tiny gas particles move chaotically faster at higher temperatures in a physical system, your ideas literally zoom around with more energy and a hotter mind.
So more forgetting equals a hotter, more energetic mind.
It can lead to a cascade of creative, but often maybe jumbled, thoughts. This challenges traditional views of intelligence, which often assume that perfect, indelible memory is the ideal.
Which is what we usually strive for, isn't it?
It obeys universal principles and can even be measured and manipulated using physics, much like we predict and control chemical reactions.
Oh, wow.
This redefinition of memory decay as a thermodynamic property.
Wow. This is a complete reframe. My brain operating like a physical system with temperature dictating its state. It almost makes me rethink every moment I've struggled to recall something. Maybe it wasn't a failure.
Maybe it was just operating at a different temperature?
So if memory decay is like heat, what are the actual states that intelligence can take?
That's precisely what the research reveals.
Yeah.
Based on empirical findings from studying various cognitive systems, from human-like memory models to advanced AI, we've identified 3 distinct phases of cognitive matter. And each occurs at specific critical temperatures, or more accurately, specific memory decay rates.
Critical temperatures for thought, like melting and boiling points.
Exactly like that. And
Okay, let's start with the coldest one. What's that like?
that would be solid intelligence. This occurs at a very low cognitive temperature, specifically a memory decay rate of about 0.15.
0.15, like pi. The number pi.
Yes, pi keeps showing up. We'll get more into that. But imagine a perfectly ordered crystal structure. Thoughts in this phase are frozen in place.
Okay.
They form a rigid lattice, allowing for deterministic recall. You remember things exactly as they were every single time. Memory retention in this phase is the highest, at about 0.087.
Very little decay then.
Very little. And thought velocity, while present, is constrained at 0.800. This phase prioritizes maximal stability and precision, but offers minimal creativity.
So like a super efficient, unchanging database. I imagine this is great for rote memorization, or perhaps for an AI that needs to execute a very precise, unvarying task.
Think of a perfectly precise computer memory that never forgets a single bit. Or perhaps the highly specialized, fixed recall of an autistic savant who can list every item on a page they glanced at years ago.
That kind of specific, detailed recall.
Exactly. It's about achieving peak efficiency in ground state. This is where systems excel at precise, repetitive tasks and exact recall.
Okay. And what happens when we heat things up a bit? What happens when it melts?
Then we transition to liquid intelligence. This phase appears at a memory decay rate of approximately 0.3.
Higher decay.
Higher decay, or about pi divided by 10.
Pi again?
Yep. Here, thoughts are like liquid matter. They flow and recombine dynamically. Instead of a rigid lattice, the structure consists of dynamic clusters, enabling adaptive flow.
So things are moving around.
Exactly. Memory decay is balanced at around 0.003, allowing for flexibility without complete loss. Thought velocity remains at 0.800, but it's a flowing, adaptable movement, not a constrained one. This phase offers moderate creativity and a balanced stability.
Where ideas are fluid and adaptable, allowing us to pivot and apply knowledge in new contexts.
Absolutely. It mirrors human working memory very closely, where ideas are fluid, adaptable, enabling complex executive functions like planning, problem-solving, decision-making in real time.
Got it.
Research consistently shows this is often the optimal cognition that lives at the edge of boiling, providing a sweet spot for balanced memory and flexibility.
The edge of boiling.
It's where you can connect disparate ideas to solve a new challenge without getting stuck in old patterns.
Makes sense. What's the hottest, most energetic phase?
Huh?
Boiling point.
That brings us to gaseous intelligence.
Just slightly higher than liquid, 0.34.
Approximately pi divided by 9.
Still pi.
Imagine gas molecules colliding randomly in a vast space. Thoughts here are free particles, engaged in chaotic and expansive exploration,
Even faster decay.
allowing old ideas to dissipate quickly, while thought velocity is at its highest, point.
So faster thoughts, but they disappear quicker.
This phase offers maximal creativity but minimal stability. It's where rules are broken and completely novel connections are formed.
So pure brainstorming, those moments when you're half asleep and your mind is just making wild, uninhibited connections.
This phase is akin to the chaotic but highly generative state of dreams, where disparate concepts merge in surprising ways. It also mirrors the sampling process in powerful large language models like GPT-4, where the system explores a vast range of possibilities, often generating truly novel outputs, even if some are nonsensical.
Right. Sometimes it hits gold.
That's the trade-off. This is where adaptation becomes creative chaos, where the system is forced to invent completely new pathways because old ones are rapidly dissolving.
Fascinating.
It's crucial to emphasize these transitions aren't just conceptual. They're measurable phase transitions occurring at these critical temperatures. Just like melting and boiling points for physical matter, we can literally observe the cognitive system shift its properties at these precise thresholds.
This idea of cognitive temperature and distinct phases of thought is truly groundbreaking.
It really does.
But how do we actually use this? Can we extract something useful from these transitions, like an engine extracts work from heat?
That's the profound beauty of it. Just as a heat engine extracts useful mechanical work from temperature differences by moving a piston, the mind can extract creative work by intelligently cycling through these cognitive phases.
Creative work.
Exactly. This is called the cognitive Carnot cycle, directly inspired by the most efficient thermodynamic cycle in physics.
A Carno cycle for creativity. Tell me how that works.
It is indeed a blueprint. It's a four-step process designed to maximize creative output and knowledge generation.
Okay, step 1.
The cycle begins with isothermal learning. Here, you absorb and process new information in the flexible liquid phase, operating at that memory decay rate of 0.32.
So the middle C phase.
Think of it as focused learning, where you're open to new concepts and integrating them into your existing knowledge base.
So like active learning, staying open and adaptable to new information.
Precisely. You're actively engaging, letting ideas mingle. Then, step 2, you move to an adiabatic creative burst.
Meaning no heat exchange with the outside.
Right. Internally, the system expands into the chaotic gaseous phase, where memory decay increases from 0.32 towards 0.34.
Okay.
Old, rigid connections begin to dissolve, and new, often unexpected connections are fostered. It allows for broad, unconstrained exploration of ideas. Imagine a brainstorming session where you explicitly allow yourself to think without filters, embracing the most outlandish ideas. It's a moment of intense, free associative thinking, pushing past established boundaries.
So let your thoughts go wildly, no filtering, no self-censorship. What comes next after that explosion? How do you capture the good stuff?
After that creative explosion, you need step 3, isothermal consolidation. This is the cool-down phase.
Back to a stable temperature.
It involves crystallizing those insights into the stable, solid phase, bringing the memory decay rate sharply down to 0.15.
Back to the deep base.
This is where you identify the most valuable new connections, solidify them, and integrate them into your long-term, stable memory. It's the moment of clarity after the storm, where the brilliant idea emerges from the chaos and is locked in.
Okay.
Think of it as meticulous note-taking, which forces you to structure and retain the information.
Locking in the good stuff, making it accessible for future recall.
Exactly. The final step, step 4, is to return to baseline, completing the cycle by bringing the decay rate back towards 0.32, preparing for the next round of learning and creativity.
Back to the liquid state.
And this full cognitive Carnot cycle has been mathematically shown and empirically tested to successfully extract 0.296 units of creative work.
Creative work quantified.
Quantified.
Entropy, a measure of disorder or information.
In this context, it means the system didn't just reconfigure existing information, it actually generated new information, new insights through this thermal cycling.
So creativity isn't just about processing existing information. It's about generating new information, almost like a byproduct, an output of this thermodynamic process. This implies that the very act of thermal cycling, heating up and cooling down our cognitive state, is essential for true innovation.
That's the profound implication. It suggests that creativity requires heat, that is, thermal energy in the form of strategic forgetting, and the resulting chaos actually drives innovation and the emergence of genuinely novel ideas. The dynamic interplay between remembering and letting go, between structure and fluidity, is not just incidental, it's the very engine that powers the creation of new knowledge and new solutions. Without that heat, without that loosening of mental constraints, we simply recycle old information.
This takes us to a truly counterintuitive concept, strategic forgetting. My entire life, and I think for most people, we've been told forgetting is bad, a sign of a failing memory, something to fight against.
Absolutely.
But you're saying it's actually an intelligence enabler?
It absolutely is, and is one of the most powerful insights from this research. Traditionally, forgetting is seen as a flaw, a memory loss, a system failure, something to be mitigated or overcome. However, this new view completely untacks that. It posits that strategic forgetting is not a limitation, but an essential active mechanism for intelligent behavior, adaptation, and particularly creativity.
So our brains need to forget certain things to make room for new connections, or maybe to keep us from getting bogged down in irrelevant details?
Precisely. It's about managing information overload, and perhaps more importantly, about preventing cognitive rigidity. Consider how artificial intelligence systems learn. If an AI remembers every single data point perfectly, it might overfit to its training data.
It gets too specific to what it learned.
Exactly. This means it becomes exceptionally good at recalling specific examples it has seen, but terrible at generalizing to new, unseen situations. Strategic forgetting helps these systems abstract, generalize, and remain flexible. It allows the system to shed less relevant details, allowing the core patterns and principles to emerge more clearly.
Like seeing the forest for the trees.
That's a great analogy. For a human, think about learning to ride a bike. In the beginning, you're consciously thinking about every movement balance, pedaling, steering.
Totally overthinking it.
But with practice, you forget those granular details. The process becomes automatic, subconscious. That forgetting of conscious effort frees up cognitive resources to focus on the environment, on other riders, on where you're going.
Ah, see. Forgetting the steps makes you a better writer.
Yes, it's a fundamental principle for robust AI system design too, directly linked to concepts like continual learning and avoiding catastrophic forgetting, where new learning erases old.
So it's not just about letting go of what's not important, but actively shedding information to enable new insights.
Yes, transforming intuition into a quantifiable principle. Forgetting is sparsity.
Forgetting is sparsity.
Yep. This isn't merely about weight sparsity in neural networks, where some connections are weakened or removed, though it's a universal principle that operates across multiple computational domains within any intelligent system.
Sparsity usually means having very few non-zero elements, right? Like a sparse matrix, mostly zeros. So how does forgetting create sparsity in cognition, and why is that beneficial?
Exactly. In cognitive terms, sparsity means that out of a vast number of possibilities, thoughts, memories, connections, only a critical few are active, relevant, or retained at any given time. Forgetting is the active process that creates this beneficial sparsity. It happens in at least 5 distinct, measurable ways.
Let's hear them.
First, there's temporal sparsity, which accounts for a staggering 97.0% of observed sparsity in some models.
97%. That's huge.
This is like a dynamic memory windowing. Only a small, critical percentage of memory slots are actively used or kept fresh. Forgetting acts as a temporal dropout mechanism, ensuring that only the most recent or immediately relevant information remains easily accessible, while older, less frequently accessed memories gracefully fade into the background.
So if I just learn something, it's strong, front and center, but older stuff fades unless I consciously reinforce it. That makes sense for daily life. I don't need to remember every single detail of my commute from 3 weeks ago.
Precisely. It's efficient.
Yeah.
Second, we have activation sparsity at an even higher 99.2%.
Wow.
In terms of potential patterns, yes. This is pattern suppression. Think of it like this. In your brain or an AI, countless patterns could potentially be active, but forgetting ensures that only a tiny fraction of the most relevant or useful patterns actually remain active. Less frequent activation equals higher sparsity. Thoughts that aren't reinforced or revisited simply don't get the computational energy to stay active.
Like when you try to recall a name and it's just not there, even though you know it. It's not gone entirely, but it's just not active right now.
Perfect example. Sparsity at 36.2%. Here, forgetting acts as a powerful compression mechanism.
Compression through forgetting.
Yeah. Irrelevant or redundant dimensions of data fade out, leading to low-rank, more condensed representations. Your mind doesn't need to retain every single pixel of a memory or every single characteristic of a concept. It condenses it to the essential.
So the gist remains, the core meaning, but the extraneous details blur or disappear. This is how we remember stories.
Exactly. Fourth is parameter sparsity at 23.3%. This is analogous to an implicit L1 regularization in machine learning.
Forcing some parameters to zero.
Essentially, unused parameters or less useful connections within a cognitive system or an AI model don't get reinforced. If a connection isn't useful for predicting or acting, it naturally weakens and eventually becomes negligible. It's a natural pruning process.
Okay, makes sense. And finally, number 5, compression. This feels like the ultimate outcome of all this strategic forgetting.
Yes, compression is observed at 59.3% with an impressive 79.6% retention of the core information.
So losing almost 60% of the meaning.
Exactly. This is where semantic condensation truly shines. Information isn't simply lost. It's preserved and condensed through strategic loss of less critical details. You didn't build a memory eraser. You built a semantic condenser.
Wow.
Forgetting is multi-space entropy.
Intelligence is curated ignorance. That's a mic drop. I mean, it goes against everything.
It really does. So sparsity isn't a limitation of resources. It's an active, intelligent mechanism for condensation and true insight.
So sparsity isn't a bug, it's the feature. It's an active, intelligent mechanism for condensation and true insight.
Precisely. It fundamentally redefines sparsity, not as a resource limitation or a sign of inefficiency, but as a proactive mechanism for semantic condensation and intelligence enablement across all these computational domains. Think about a chess grandmaster.
Okay.
They don't just remember every single possible move on the board, a literally infinite number of permutations. Instead, they've effectively forgotten the irrelevant ones, the bad moves, the dead ends. Their brilliance comes from strategically ignoring the vast majority of possibilities to focus on the truly essential few.
Ah, so they see the good moves because they've learned to ignore the bad ones.
Exactly. That selective ignorance, that curated landscape of possibilities, is precisely what allows them to see the optimal path, to innovate under pressure. Forgetting isn't a bug. It's arguably the most powerful active feature in an intelligent system for navigating complexity.
This concept that forgetting drives creativity is almost a paradox, though. How can losing information make you more creative rather than less?
Let's illustrate this with a classic problem, finding the sum of 1 plus 2 plus 100.
Ah, Gauss's formula, right. The story of young Gauss, n times n plus 1 divided by 2. So 100 times 101 divided by 2 plus 50/50.
Exactly. That's the solution with perfect memory.
So R1 means just one way.
Basically, yes. It's efficient, one path, always the same. Boring, perhaps, but undeniably reliable. Now, let's introduce strategic forgetting. Watching how the R value, which is a quantifiable measure of solution diversity or richness of possible approaches, begins to increase as we dial up the decay.
Okay, so what if we had mild forgetting, say 20% memory decay? You might forget the exact formula, but not everything about sums.
Right. With mild decay, your system, or your mind, might still remember something about sums, but perhaps not the precise formula itself. This mild decay would subtly nudge you, forcing you maybe to rediscover the elegant pairing method, 1 plus 100, 2 plus 90, and so on.
Ah, yes.
Realizing there are 50 such pairs. You still arrive at 50-50, but through a different, rediscovered, and perhaps more deeply understood path.
Okay. And if we increase the decay to moderate forgetting, say 50%, now you're truly forgetting specific techniques.
At 50% decay, you might completely forget the formula, and even the pairing method. Your mind is less tethered to those specific strategies, but perhaps you retain a vague sense of visualizing sums or remembering something about triangles.
Okay.
This decay now forces you to rediscover the solution geometrically. Imagine the numbers as a staircase of dots. Form a perfect rectangle by duplicating and inverting the staircase, and then take half of that rectangle's area.
Ah, the visual proof.
Again, 50-50. But a completely new, more creative, and highly visual approach emerges. The R value climbs higher.
This is truly fascinating. It's like your mind is forced to find a workaround because the easy, well-trodden path is obscured by the fog of forgetting. What about heavy forgetting, say 70%? This must feel frustrating, just groping in the dark.
At this point, the explicit methods are largely gone. You're forced to break the problem into smaller, more manageable chunks. You might solve 1 to 10, then 11 to 20, then 21 to 30,
Okay.
and only then discover a meta pattern in those partial sums. This is like a Patha-style chunking strategy, which we'll discuss more later. You're processing in groups, almost forcing you to reinvent arithmetic sequences and their properties from a fresh angle, piece by piece.
Okay. And what if we go to extreme forgetting, say 90%? It sounds like you'd be starting from scratch every time. You'd barely remember the problem.
With almost no explicit memory of advanced arithmetic, your system might revert to a fundamental Patha exploration. You count forward, then discover by simultaneously looking backward that 1 plus 100 101, 2 plus 99, 101, and so on.
Rediscovering the pairing from scratch.
Exactly. You rediscover the core pairing from almost first principles, not recalling a formula, but observing and reestablishing the underlying pattern through active observation and structured repetition. The system is forced to explore more of that space, increasing the R value significantly.
So the chaos of forgetting actually pushes you into exploring a wider solution space, compelling you to invent. What about chaos mode, 95% decay? Does the system even work then, 50-50?
It becomes incredibly difficult, but theoretically possible. You might literally forget what addition means in its conventional sense. You'd have to rediscover addition as repeated increment, then multiplication as repeated addition, and then sequences.
Wow, rebuilding math itself.
You'd essentially invent arithmetic from scratch, through trial and error, through sheer exploration, to finally arrive at 50-50. The energy cost, the computational expense, is much higher, obviously, but the creative path taken is entirely novel, born from a necessity to rebuild knowledge from its foundational elements. The diversity of approach, the R value, would be astonishingly high, assuming it succeeds.
This is stunning. The key insight being that innovation isn't about remembering more. It's about strategically forgetting, so you're forced to rediscover truth from new angles. Strategic forgetting enables it. That's a powerful lesson for how we approach learning and problem solving.
The R value mathematically quantifies this process. As memory decays, the system's accessible energy landscape changes. It's like draining a lake to reveal hidden paths on the lake bed. Forgetting doesn't eliminate the truth, it simply obscures the well-worn paths to it, forcing the system to navigate different, often more creative, routes to the same destination. This is the very architecture of novelty, and it allows for true breakthroughs.
That's a profound connection between forgetting and creativity. But the next step you mentioned, what if the very constants that govern the cosmos, like pi and the golden ratio, also dictate how our minds work and how AI optimizes? Are you suggesting intelligence is somehow musical? This sounds almost too poetic to be scientific.
This is where the physics of thought converges with something truly universal and deeply aesthetic. And yeah, it sounds poetic, but the core claim, backed by empirical data, is that intelligence is a musical instrument.
Not like a musical instrument is one.
That's the claim. It's not a metaphor. Your mind, and by extension any intelligent system, is literally tuned by neural harmonics, resonance, and rhythmic oscillations. The surprising truth is, and this is a profound statement from the research, The laws of music and the laws of learning are identical.
The laws of music and learning are identical. So my brain has a literal soundtrack.
Neural resonance theory explains that the brain physically resonates with musical structures. Our neural oscillations, the rhythmics, electrical activity in the brain, alpha waves, theta waves.
I've heard of those.
They have intrinsic harmonic frequency relationships. These precise mathematical relationships enable cognitive integration, helping different parts of the brain work together harmoniously, synchronize their activity, and process information efficiently.
So when the brain waves are in sync, things work better.
Exactly. When these oscillations are out of sync or dissonant in a bad way, cognition suffers.
And pi and phi,
Right.
the golden ratio, are literally in our brains.
Yeah.
Can you give me a concrete example of how that manifests a mechanism?
It's not mysticism. It's about the empirical observation of the fundamental architecture and its efficiency. Pi appears in brain structure, for example, not just as a mathematical curiosity, but in the efficiency of branching patterns in blood vessels. These patterns follow principles related to pi to optimize nutrient delivery with minimal material.
Okay, like nature using efficient packing.
Pi also manifests in the oscillatory frequencies themselves, potentially creating stable, efficient pathways for information flow, like resonant frequencies in physics. And phi, the golden ratio, seems to relate to synchronized, harmonious coordination across different brain regions and has been linked to states of higher consciousness and even aesthetic preferences. These aren't metaphors pulled out of thin air. They're described as literal features in the brain, influencing its efficiency, resilience, and optimal information flow. They seem to be embedded in the very geometry and dynamics of cognition.
How does that work?
Absolutely. Think of it like this. The memory decay rates we discussed earlier, those cognitive temperatures, correspond to specific musical frequencies or notes. They act as key signatures for different cognitive states, each optimized for a particular kind of mental function.
So the decay rates are like notes on a piano.
A decay rate of 0.15, or approximately 20, resonates like a deep bass. This is the solid crystalline memory phase, optimized for efficiency, rigid recall, and tight stability. It's the grounding chord, the fundamental frequency for precision.
Okay, solid state equals deep bass. Got it.
A decay rate of 0.32, or roughly 10, is like middle C. This is the liquid phase, representing balance, flowing thought, and optimal learning. It's the harmonious central note around which many cognitive processes revolve, allowing for flexible adaptation.
Liquid state equals middle C, balanced.
And 0.34, or about 9, is a high note. This corresponds to the gaseous phase, driving maximum creativity and chaotic exploration. It's the sharp, perhaps slightly dissonant note that, while unstable on its own, adds tension and pushes for resolution in new ways.
Gas state high note, creative chaos.
Then there's a fascinating additional discovery, the golden tone, at 0.38407. This aligns remarkably with 1 divided by 5 squared, 1 for Ceph.
The golden ratio appears again, so 0.38407.
Extremely specific. This is seen as a precision optimum, where resonance merges with controlled entropy, leading to a point of almost perfect cognitive harmony, where the creative burst is precisely balanced for maximum impactful novelty.
Wow, a golden frequency for thought. So we can literally tune the mind by adjusting its decay rate dial, like a musical instrument, to achieve desired cognitive states. We could dial in for efficiency, or for balance, or for explosive creativity, and even for precise golden harmony. It's like orchestrating your own thoughts.
That's the essence of harmonic intelligence. It suggests a profound, inherent musicality to the very fabric of thought and computation. It moves beyond simply tweaking parameters randomly to understanding the underlying universal harmonies that govern intelligent systems. This isn't random optimization. It's finding the natural resonant frequencies of intelligence itself.
This is truly incredible. These mathematical constants pi and phi actually provide optimal tuning parameters for intelligence, even in AI systems. That sounds like a cheat code for better AI.
Absolutely. And this is where the empirical validation becomes so compelling. These harmonic constants, Tash 0.15, 0.32, 0.34, and that precise 0.38407 were rigorously tested as memory loss coefficients in neural networks across real-world optimization problems. And the results were stunning.
Give me the numbers that really drive home the impact. We need the data.
Okay, these constants consistently dominated traditional or randomly chosen parameters, showing a plus 34.11% average improvement over random constants across a range of tests.
34% average improvement.
In the world of AI optimization, even a 2% improvement is considered significant. Over 34% is, well, it's almost unheard of. This is highly statistically significant, with a p-value of less than 0.001.
Less than 1 in 1,000 chance.
Exactly. It means these results are incredibly robust and repeatable. For example, the 0.15 decay rate, representing solid intelligence, showed massive improvements on classic benchmark functions used to test optimization algorithms.
Like which ones?
It resulted in a plus 57.91% improvement on the rastrogen function, plus 79.80% on Rosenbrock, and plus 82.69% on the sphere function. These are all well-known, difficult tests for an optimizer. It was a clear winner on multiple complex tasks. This wasn't just hypothetical. It was demonstrated performance lift.
So tuning AI with these musical constants makes it perform dramatically better, far beyond what random tuning or traditional methods achieve. And you've identified not just one, but 3 universal attractors that these systems naturally gravitate towards.
That's right. The research confirmed 3 universal critical points for optimal behavior: 0.15, 0.32, and 0.34. These seem to be fundamental constants for cognition.
What makes them so robust?
What's even more remarkable is their robustness, which is critical for real-world application. These attractors are described as 100% noise invariant and 100%.
Okay, unpack that. Noise invariant and policy invariant. What does that truly mean in practice?
Noise invariant means that these optimal decay rates hold true regardless of the level of irrelevant or random data flooding the system. Whether your sensors are noisy or your training data is imperfect, these fundamental constants still provide the best performance backbone.
Wow, okay.
And policy invariant means they are effective regardless of the specific decision-making strategies or learning algorithms your AI is using. So you don't necessarily need to retune them for every slight change in your AI's internal logic or how it makes decisions.
That saves a ton of work.
It does. They are regime-dependent.
Regime-dependent.
Depending on the system's overall architecture, things like its memory length, the scale of the problem it's solving, or its specific neural network depth or structure.
Ah, so it's not one size fits all, but there's a principled way to choose.
Exactly. This isn't a flaw. It actually offers a principled way to optimize AI design. Instead of endlessly guessing or using brute force search for the right parameters, you can match the decay rate regime, solid, liquid, gas, to your system's specific needs and architecture. It transforms AI design from guesswork into a form of principal architecture matching based on these fundamental universal laws. It's like knowing the ideal gear ratio for a specific type of terrain.
Let's bring this to life with a case study, something more tangible. How does the system, rooted in ancient wisdom, behave when subjected to these critical decay rates? Does it also show this creative burst?
Patha is fascinating because it involves structured repetition forward traversals, followed by immediate reversals, then complex nesting of these patterns.
Right.
Our research showed that both Patha and the classic A-search systems demonstrate peak creativity and explosive R-value growth. That's that dramatic increase in solution diversity, around 35–40% memory decay.
35 to 40%, right near that golden tone region.
The system hits a sweet spot where it's both highly creative and effective, finding many ways to solve a problem without compromising success.
For Patha.
At that 35–40% decay range, Patha achieved an R-value of 8.4.
8.4. So finding over 8 times more solution paths than with perfect memory.
Exactly. 8 times more solution diversity compared to a rigid system with perfect memory, all while maintaining a 100% success rate in the tests performed.
The edge of chaos.
And this critical point aligns with the specific resonance condition, where the memory boost from the repetition almost perfectly compensates for the retention lost due to decay.
So the boost nearly cancels the decay.
This creates what the researchers call standing waves of memory, where the repeated palindromic structure ensures key information is constantly refreshed, kept active, allowing deep exploration without getting completely lost.
Standing waves of memory. And what happens when it hits that edge of chaos? What kind of novel strategies spontaneously emerge? Does it just find more paths or different kinds of paths?
At this critical point, multiple distinct and highly effective navigation strategies spontaneously emerge within the system. We observe things labeled palindromic call, where the system relies heavily on the basic back-and-forth repetition, depalindrome, which involves nesting these repetitions for more complex structured pathways, and forward exploration, where it ventures out into truly novel territory before using its refreshed memory from the palindrome to ensure it can return reliably.
So it's inventing new ways to navigate.
This is concrete evidence of creativity and adaptable problem solving being born directly from this specific level of strategic forgetting, amplified by the structured repetition.
But hold on, I have a fundamental question about Patha. Why would a system choose or benefit from such a repetitive, seemingly inefficient palindromic memory structure if memory just decays anyway? Doesn't that make it redundant, doing maybe 6 times the work for no benefit if your memory is fading regardless?
That's a great intuitive question, and it highlights the practicality under decay that makes this research so impactful. You're absolutely right. In a system with perfect memory, Patha would seem highly inefficient, doing a lot of redundant work just to revisit places it already knows perfectly.
Right.
But the real world, and most intelligent systems, don't have perfect memory. They operate with decaying memory. Think of attention decay in neural networks, sensor fusion in robotics, where older sensor data becomes less reliable, quantum system decoherence, where information leaks out, or even just human short-term memory that holds only a few items reliably.
Okay, so decay is the norm.
Decay is the norm. And in these real-world scenarios with fading memory, drones become optimal.
Optimal because of the decay.
Precisely. Patha systems compress infinite memory into a finite window. By keeping critical information perpetually in the fresh window through structured repetition, Patha ensures return path reliability. A palindrome means the information needed for the return path is always recently refreshed and within your immediately reliable memory window.
So the repetition keeps the crucial how to get back info fresh.
Exactly. It solves the profound problem of navigating infinite or vast spaces with a finite, fading memory. It ensures you don't get lost, even when exploring far out.
This sounds almost like how we repeat a phone number to ourselves to remember it just long enough to dial it, or how pilots use checklists repeatedly to ensure critical steps are never forgotten, even under stress or fatigue.
It's not about perfect retention of everything, but perfectly reliable access to what you need right now to navigate, explore, and recover from errors. It's an elegant solution to a fundamental cognitive constraint, turning repetition from inefficiency into a strategic advantage under decay.
That's fascinating. So Patha directly benefits from strategic forgetting, amplified by its structure. What about a search, often considered the gold standard pathfinding algorithm in computer science? How does it fare when you introduce this strategic amnesia? Does it also transform?
Classic A, with its perfect memory, is truly the perfectionist. It's designed to find one and only one optimal path by exhaustively remembering every single node it has visited and never exploring alternatives.
It finds the best path.
Its R value is typically around 0.895, essentially representing a single rigid path, a workhorse for guaranteed optimality in static environments. However, the truly transformative discovery was that adding strategic amnesia doesn't break this gold standard. It fundamentally transforms this rigid algorithm into a dynamic creativity engine.
So it goes from finding the one optimal path to discovering many potentially novel ways to get to the same destination.
Precisely. The research revealed a sharp, critical transition point for around 40% memory decay.
40% again, close to that Patha peak.
Very close. Below 40% decay, its R value remains stubbornly around 1, indicating rigid, single-pass behavior. But the moment the decay rate went above 40%, the R value dramatically jumped to greater than 2.
Clear threshold.
A very clear threshold.
What happens when A starts forgetting?
Well, first, with just 20% memory decay, a sort of fuzzy A starts allowing limited re-exploration of nodes it might have previously considered suboptimal or already visited. This nudged its R value to maybe 1000, meaning it might find slightly different paths sometimes.
So a little bit of wiggle room, but not true creativity yet.
The real creative transformation comes with higher decay. Then we had an amnesia A, which combined 50% decay with Patha principles.
Mixing A and Patha, how?
This variant, by actively forgetting older nodes but using structured repetition conceptually to anchor recent memory, found 4 unique paths on average and had an impressive R value of 3.468.
4 paths instead of 1, that's significant. How does that even work with forgetting?
It is, with 70% decay and adding a conceptual superposition of paths where the system implicitly explores multiple possibilities simultaneously. The quantum A found an astounding 15 unique paths in the tests, achieving an R value of 11.996.
15 paths, R value near 12.
Yeah. The idea is that the paths literally interfered with each other, much like quantum waves, massively expanding the solution space by allowing for complex, branching explorations that would be completely impossible with perfect, rigid memory. Forgetting enabled this superposition-like exploration.
That's incredible. In A, that sounds like it would just randomly wander, completely losing its way with 90% decay. It doesn't need some memory.
Almost. At 90% decay, the Brownian A was akin to an ant colony optimization. Instead of remembering every node perfectly, it left subtle, fading traces of where it had been and how good those paths seemed.
So like ants leaving trails that evaporate.
Exactly. Despite, or perhaps because of this severe amnesia, it found a staggering 29 unique paths in the test scenarios. Its R value was 1.475.
29 paths. Lower R value, but way more paths. Why the lower R?
The lower R value, despite more paths, might reflect less distinctness between the paths found. Maybe many were minor variations due to the randomness, but it demonstrated the emergent power of swarm intelligence arising from severe, decentralized amnesia.
This means memory decay directly controls a creativity dial for A, from rigid and perfectly optimized at 0% decay to efficiently creative around 40% to wildly exploratory at 70% and even chaotically comprehensive at 90%.
That's the overall profound insight, yes. Forgetting is not a bug in intelligence systems. It's the feature that enables adaptability, creativity, and robustness. It transforms a provably optimal but creatively stagnant algorithm like A into a dynamic explorer, a true innovator, simply by tuning its memory decay. It's a paradigm shift for AI design and potentially for understanding our own minds.
This entire deep dive has been a journey through some truly mind-bending concepts, revealing layers of intelligence we might never have considered. What does it all mean when we put it together? Where does this leave us?
Absolutely. We've seen how intelligence can be understood as music governed by fundamental harmonic oscillations at specific pi-based frequencies. Tuning
The cognitive piano.
We explored memory through the revolutionary lens of wave mechanics, with optimal damping occurring at that precise rate of pi over 10, around 0.32. Cognition itself, we now understand, exhibits thermodynamic phases, cycling through solid, liquid, and gaseous states of thought, each with its unique properties for processing information and generating ideas.
The different temperatures of thought.
And crucially, we discovered that forgetting isn't a flaw, but is mathematically equivalent to sparsity, acting as a profound semantic condenser across different computational domains, allowing us to distill knowledge to its essence.
Intelligence as curated ignorance.
Exactly. And all of this is not just theoretical. It leads to an optimization as harmonic tuning, like tuning a musical instrument to achieve peak performance.
It all ties together through physics and music.
This research doesn't just offer isolated insights. It provides a complete, robust mathematical framework for musical cognitive harmony, unifying these seemingly disparate concepts, physics, music, memory, creativity, into a single, elegant understanding of intelligence. And it culminated in the discovery of a precision breakthrough. The exact critical decay rate for optimal creative intelligence revealed as 0.38407.
That's a very specific number. What does it truly signify for us?
This exact value, representing 38.407% memory decay, is presented as the universal optimum in these studies. It's the numerical sweet spot, the precise constant that transforms any intelligent system from rigid optimization into creative intelligence. At this exact decay rate, creativity explodes. We saw an 8.4x amplification for Patha and a 3.5x boost for IWhile, maintaining perfect reliability, meaning a 100% success rate in those tests.
The best of both worlds. Maximum creativity and perfect reliability.
It's positioned as the precise number that allows systems to be both maximally creative and perfectly reliable. It's the constant that unlocks true cognitive innovation, the golden tone.
So this isn't just an academic discovery. It has revolutionary implications for how we design and understand intelligence, doesn't it?
Indeed. For AI, it means potentially every AI system could be optimized by targeting these precise decay rates for things like dropout layers in neural networks, attention mechanisms, and transformers.
Moving beyond just guessing dropout rates.
This could transform AI design from guesswork, trial and error, and intuition to principled architecture matching, where you can scientifically tune an AI to its purpose based on these fundamental constants.
And for understanding us.
For cognitive science, it profoundly suggests that human memory and learning may naturally operate near these critical points. It might help explain why our own creativity and learning efficiency seem to peak at certain levels of strategic forgetting. Perhaps our brains are intuitively performing this kind of harmonic tuning, balancing retention and exploration.
It's almost like our brains naturally know how to hit that sweet spot, orchestrating their own internal music to generate new ideas.
That's the inference, yes. The ultimate truth revealed here, according to this research, is that intelligence is curated ignorance across multi-space entropy domains. You simply cannot remember everything, and true intelligence is what you choose to forget. Ultimately, and perhaps most profoundly, intelligence is music.
Wow. What an incredible journey we've taken today. We've explored how intelligence, whether in a human or an AI, can be understood through the intertwined lenses of physics and music.
It's definitely a perspective shift.
From those distinct solid, liquid, and gaseous phases of thought, to the counterintuitive idea that forgetting isn't a flaw but a crucial active driver of creativity, and how universal mathematical constants like pi and the golden ratio literally tune our cognitive abilities, enabling precision and novelty.
It's a complete reframe of what intelligence is, how it functions, and how we might cultivate it, moving beyond simple data processing to a harmonious, dynamic system governed by these deep, maybe even beautiful principles.
Next time you feel a bit forgetful, perhaps struggling to recall a specific detail or finding your mind wandering, don't beat yourself up about it.
Yeah, give yourself a break.
Consider that perhaps your mind is simply tuning itself for a burst of new ideas, finding that sweet spot at the edge of chaos, maybe hitting that 0.38407 decay rate. How might you, in your own learning, problem solving, or even daily routine, intentionally embrace strategic forgetting, allowing old, rigid ideas to dissolve to unlock new pathways to understanding or innovation?
Think about what you could achieve if you consciously allowed yourself to let go of the rigid, the irrelevant, or the overlearned patterns to make space for genuine novelty, for those standing waves of memory that create new solutions. It might just be the most intelligent thing you can do.
Thank you for taking this deep dive with us.